We are still on Unit 0. We are covering Module 0.6. In our last video lecture, we talked about correlational data, and when we look at how two things move in conjunction with one another, whether if one moves up, the other moves down, or as one moves down, the other moves up, or they move together, was one move up, the other one moves up. We talked about what is correlational data, how to interpret correlational data, and what does it mean, what can it tell us. This video lecture is going to focus more on statistical data. We're going to look at more of the stats, more of the numbers, and how can we interpret numbers? How do we share numbers? Why are there so many numbers? And what do we need to be careful of as a good consumer of numeric research? So the first type of numeric we're going to talk about is a type of descriptive statistic called a bar graph or a histogram. So when we look at descriptive statistics versus inferential statistics, what we mean by that is descriptive statistics merely are, what are the numbers? What do the numbers say? What is the bar graph? What are the measures of central tendency? What is the standard deviation? What is the mean, median, and mode? Those types of things. Descriptive statistic just means tell me the data. Inferential statistics, we're going to talk about later in this video lecture, is how can we interpret them? What meaning do they have? So when looking at descriptive statistics, one way in which we can share our data is through a bar graph or a histogram. This is merely where we might indicate maybe we are looking at the number of people who choose option design A versus option design B versus option design C. And so we might, again, maybe we have a naturalistic observation and we are looking at how many people take a cookie from cookie group A versus cookie group B versus cookie group C. And I might put on a bar graph or a histogram the number of people that chose cookie A, number of people who chose cookie B, number of people who chose cookie C. One thing we want to be very careful of in being consumers of bar graphs is the scales in which are used on bar graphs. If you take a look at this picture right here, you can see the same exact data comparing A, B, and C, i.e. 32, 38, and 35. But the bars themselves look very different. When we have a scale that is much larger versus a scale that is much smaller, we see a more significant difference between those bars. So it's really important that when we're consumers, we look at the numbers, right? We look at 32 versus 38 versus 35. That is a pretty close tie between those three. But if I were to instead spread out my data numbers and make it look like my bars are significantly different, I might be trying to communicate a different story to my readers or my consumers of research. So make sure we always look at, what does that scale look like? What is that telling us about that bar graph? We see the same thing here. So perhaps I'm sharing about how the percentage of functioning of different trucks are in the past 10 years. Again, depending on the scale I use, tell a very different story. In the bar graph on the left, it looks like their brand is significantly better than the other one. So why would you not buy that truck? But if we look at it on the right-hand side, when we change that scale again, we see that there's really very little difference between their brand and brand X, Y, and Z. So when being a consumer, look at that scale. Are they trying to convince you of something? And are they doing that by kind of changing the scale to make it look more dramatic than it actually is? Another three forms of descriptive statistics is what's called our measures of central tendency. And we have multiple measures of central tendency. We have our mean, our median, our mode, bimodal, as well as range. So, or bimodal, sorry. Our mean is our average. This is our statistical average. This is if we take all the numbers in our data set, divide them by the number of numbers in the data set, whatever number that is, that's our mean, our average. Our median is our middle number. If I took all of my data set numbers and I put them in order from lowest to highest and I crossed off the ends. Whatever number I ended up with in the center is my median. It's my middle number. I have my mode, which is my most common number or my most common data point. So if we look at these letters in here, the mode would be an A because there's one of each of the other letters, but there's two of A's. Sometimes you might also find a bimodal where you might find that a data set has two modes, in which case you might see two peaks in a histogram. And finally, we have our range. Our range is our average from the top to the bottom. So if we have, let's say we are a teacher and we are taking in every single student's score on their last unit test, the mean would be the average of all the scores divided by that 100. The median would be the very center score. If I took all of my students, highest to lowest, my very center score would be my median. My mode would be the most common score given. And my range would be the lowest score to the highest score. So let's take an example of a very simple data set, 1, 1, 3, 5, 6, 8, and 9. Okay, my mean, 4.7, because I took those numbers, divided them by 7, got 4.7. My median, my middle number, I crossed off the outliers. My middle number is a 5. And here we only have one mode, which is a 1, because there's only one most common score. So our question is, why do we need all these numbers? Why do we need especially a mean and a median? Because they seem to be telling us the same thing. That mean is a 4.7, the median is a 5. Why do we need to have the average and the middle? Well, that's what we're going to talk about today. Let's take, for example, we have a baseball card collection. And this is all of my baseball cards. So you can see the name of the baseball player on the left-hand side, and the right-hand side, we can see how much that baseball card collection is worth. Sometimes the mean and the median can give you a much different picture of your data. And if you're not given the mean and the median in your data, sometimes you don't know that you are being duped. Sometimes you don't know that the person who's sharing the research is only sharing with you certain pieces of information. So let's say, for example, this person is trying to get the Kane County Fairgrounds to allow them to sell their baseball cards there. And they know that it will be more appealing if they have a better card collection. So if they told the Kane County Fairgrounds that their average baseball card was worth $74.14, would they be being honest with the Kane County Flea Market? And the answer is, yeah. Their average is $74.14. If I add up all of those baseball cards, divide by the number of baseball cards, my average is $74. But am I being clear? Am I giving the Kane County Fairgrounds a clear picture of really what my baseball card collection is? Because if I were to just take out my one outlier, Nolan Ryan, my mean is now 2.85, which $2.85 is a much better or more accurate representation of my data. So it's really important when we are reading data or when we're providing data and sharing data that we know the mean and the median. Because if the mean and the median are not close to one another, we know that there must be some outlier. There must be something that's either pulling that mean up or dragging that mean down. But if that mean and median are not right near each other, we know there's got to be some outliers. And so sometimes people, use this to their advantage. You also might find when you drive by new neighborhoods, oftentimes on the signs of new neighborhoods, it will say median home price is instead of mean home price. And the reason they do this is because they are looking to get the right type of people into their housing neighborhood, into their neighborhood. So for example, let's say that all of these little data points indicates how much that house is worth. So 150,000, 200,000, 250,000, 300,000, and so on and so forth. If I were to say that my average house price is $700,000 in this neighborhood, would that be giving an accurate picture and pulling in the right type of buyers into my neighborhood? I hope through looking at this, you would say no, because most of the houses are under 500,000. But if we give the mean, we're going to be sharing a much different picture. So that's why they oftentimes say the median, because they really want to go to that center number to make sure that they pull the right crowd to come in. So sometimes in magazines and newspaper articles, on TikTok, in the news, they may give you a picture that fits their agenda. They might tell you a mean without a median. They might give you a median without a mean in order to fit the agenda of what they're trying to communicate. So it's your job to be a good consumer and to know and ask the right questions to get all the data points to really know the big picture. So what other data can we get besides just these mean, median, mode, range? What other data can give me another picture of research findings? So let's take, for example, you are a teacher, and let's say you have your first hour class has an average of 80% on their last unit test, and your second hour class has an average of 80% on their last unit test. Looking at just the mean, let's say that the median is very close as well. Is there any other way that I can tell if my first class or my second class is doing better? And the answer to that is yes. There's another piece of data that could give me an idea of the difference between how class 1 versus class 2 is performing. And that's through a number called the standard deviation. Your standard deviation is the number that tells you how far spread your data is from the mean. Your standard deviation tells you how far spread your data is from the mean. Or another way to think about it is your standard deviation tells you how consistent are your scores. Are your scores clustering around the mean where most people hang out around that mean? Or are your scores really far that most students don't cluster around the mean and the data is really far spread? So let's delve into the standard deviation a little bit more. Be ready to draw. You should have some pictures as you are listening to this. So when we look at drawing a bell curve, we look at certain information that goes on a bell curve. When we apply data to a bell curve, we want to first start by drawing a normal bell curve like you see here. In the center of that bell curve should be the mean. So in this case, let's say our class average is a 75%. I'm sorry, not an 80. You are going to put a 75 right smack dab in the middle because that's your average. Let's say class 1 has a standard deviation of 5 and class 2 has a standard deviation of 10. We want to plot those. So class 1, average of 75, standard deviation of 5. If I plot that, 1 standard deviation above the mean is an 80, 2 is an 85, 3 is a 90. 1 below, minus 75 minus 5 is 70, 70 minus 5 is 65, 65 minus 5 is 60. There's one bell curve, and we'll talk in a second about what we can learn from this bell curve. So that's 1. Draw that bell curve. Okay, this is class 1, standard deviation of 5 with an average of 75. You're plotting 3 standard deviations above and 3 standard deviations below the mean. Class 2, same average, 75, this time a standard deviation of 10. You want to plot, again, 3 standard deviations above the mean, 3 standard deviations below the mean. So 75, and 85, 95, 105, 65, 55, 45. So this is class 2. Pause the video, get those drawn. Then I want to ask myself, what data can I glean from this bell curve? So there are certain things we know about bell curves. There are certain things we know about standard deviation. One of those things that we know is that our data, if you look 1 standard deviation below and 1 standard deviation above the mean, 68% of my data points fall within that area. 95% of my data fall between 2 standard deviations below and 2 standard deviations above. And 99% of my data fall between 3 standard deviations below and 3 standard deviations above. So if I am plotting a mean with a standard deviation, I can draw some conclusions about my data, about my class. So let's go back to our class. Looking here, class 1. If I know 68% of my data falls between 1 standard deviation below and above, that means class 1, 68% of my students scored between a 70 and an 80 on this unit test. 95% of my students scored between a 65 and an 85. And 99% of my students scored between a 60 and a 90. Looking at class 2, I can do the same conclusions, different numbers. 68% of my data fall 1 standard deviation below and above the mean. So 68% of my students scored between a 65 and an 85. 95% of my students scored between a 55 and 95. And 99% of my students scored between a 45 and a 105. So all of a sudden, I have a new understanding of my class average. And if I'm to decide which class did better, I'm going to say class 1 with a standard deviation of 5, because most of the students scored closer to that average. They clustered around that mean. They were more consistent. I didn't have as many outliers. 99% of my students fell in a much smaller area than in class 2, where 99% of my students fell in a much larger area. So standard deviation tells us how close or far spread our data is, i.e., how consistent our data is. Once again, standard deviation tells us how close or far spread our data is, or how consistent it is. So if given the information, mean and standard deviation, you should be able to plot it on a normal bell curve, and you should be able to draw 3 conclusions using your numeric data. 68%, right? 95%, and 99%. This is assuming that we fall on a normal bell curve. Sometimes, again, if we have some outliers, we might find that this curve is skewed. So there's positively skewed data and negatively skewed data. And what I want you to think about is where the tail is. So if the tail is in the positive, it's positively skewed, meaning there are outlier scores that are pulling the data in the positive direction. This is where my median is below my mean, because I have an outlier score over here that is pulling my data set. In contrast, I might have a negatively skewed. Again, I'm going to look at the tail. The tail is in the negative direction. I have some low scores that are pulling my data this direction, where my median is higher than my mean. So in a normal bell curve, it's evenly split 50-50 from the mean. The mean and the median are the exact same or close to. If the mean and median are the exact same and we get that standard deviation, we're able to draw those conclusions that we talked about. If we have a data point that pulls us in a positive direction, it pulls us over to the right, that means that my mean is higher than my median because it's being pulled by higher scores. In contrast, if it's negatively skewed, that means my mean is lower than my median because my mean is being pulled in this direction by lower scores. So that's differential. That is right here, that is our descriptive statistics. So the way we can express data, we can share data through a bar graph, we can share data through the measures of central tendency, we can share data through our standard deviation, we can interpret data using standard deviation and bell curves. We know what it means if the data is skewed. We know how people manipulate data. That's our descriptive statistics. That is merely us sharing our numbers with each other. The second piece that researchers do is they have to understand the inferential statistics. So not only do they have to look at those numbers, they have to understand how those numbers can be manipulated. They need to look at the whole picture of all the numbers to really get an idea. But then they have to decide, can those results be generalized to a larger population? Are these results that we found in our experiment, can I take those results and apply those to a larger group? If I conduct an experiment, I need to make sure that my results can be generalized to the larger population. Otherwise, I'm not going to post my results. And something like a case study can't do that. We can't generalize our results to a larger population because we're only studying a small group. So this is when we're talking about experiments only. Can we generalize these results to a larger population? So in order to say yes, we kind of need to ask ourselves kind of two questions. Is it reliable and is it significant? By reliable, I mean, when we are looking at our data, when we're looking at the descriptive statistics, we want to ask ourselves, were those statistics based on a representative sample? Or do we have a bias sample? Did we do an accurate random assignment? Did we make sure we had a large enough sample size that we pulled from? Large samples are always better than small. Do we represent the population well with the participants we had in our experiment? Did we have a lot of participants, not just a small group size? And finally, we also want to ask ourselves if it's reliable, is looking at, did we do a meta-analysis? Did we look at our replicated study? Did we look at the data from all of those replicated studies? Or are we taking the data just from one study that was conducted? So, does it represent? Is it not a bias sample? Is it a large sample? And does it have data from multiple replicated studies? Or are we just looking at one study? If we can say yes to all those things, hey, we are in good shape. Our next question we have to ask ourselves, is the difference significant? So in here, we ask ourselves the difference between whether or not it's statistically significant or not, as well as we have to look at the effect size and whether or not it has practical significance. So there is a p-value score that you are never going to have to calculate, but you're going to have to understand what it means. P-value just means, is the data statistically significant? Meaning, is the results we found not likely due to chance? If our p-value is less than or equal to 0.05, what that says is that there is a 5% or lower chance that these results happened on accident or happened by coincidence. So you won't ever have to calculate that, but you want to understand that this p-value lets us know, is this data statistically significant? Does this data mean that there is actually a difference between the experimental condition and the control condition? Do we see that there is a less than 5% chance that the results, the difference in results between the control and the experimental group are not due to chance, that they are due because of that independent variable I tested? That's the first thing. Did I get a p-value of less than or equal to 0.05? If I do, fabulous. Well, then I want to ask myself, well, what's the effect size? So let me give it to you in an example format that might help. So let's say that I am doing research on whether or not an app helps you to sleep longer at night, get more sleep, okay, get more REM sleep or whatever it might be. Let's say my p-value shows that 0.03, that it is statistically significant. There is a mathematical difference between the control and the experimental condition. Well, then I want to ask myself, what is that difference? That's the effect size. Let's say the effect size is 5 minutes, that there is a statistically significant difference between the experimental control condition, that the experimental condition got 5 more minutes of sleep than the control group. I'm going to ask myself, okay, well, does that matter? Is that worth the time it's going to take and the money it's going to take to download, pay for this app, do all the meditation that it's asking me to do for 5 more minutes of sleep? That's where you ask yourself, what is the practical significance here? So if you're given the p-value, if you know it has statistical significance, you know that mathematically there is a very small likelihood that the results were due to chance, that those results are good. Then you have to ask yourself, what's the effect size? What is that difference between the experimental and control condition? Is the effect size 5 extra minutes of sleep? If that's the effect size, you ask yourself, is it worth it? Maybe you're looking at a weight loss drug, right? A weight loss medication. Many weight loss medications say that there's statistical significance, that if you take this pill, you are going to lose more weight. And if my p-value is less than 0.05, that means that mathematically, yes, there is a difference between the experimental and control condition. But then I want to ask myself, what is the effect size? Is the effect size a half a pound? If it's a half a pound, then I have to think about the practical significance and say, is it worth maybe the stomach aches or the side effects from this drug for a half a pound over a 3-month period? So we want to make sure that we are evaluating, yes, is it statistically significant? But then what is that effect size? How much significant difference do we see between those two groups? My hope for you after this video lecture is that you were able to be to understand how to describe data, how to interpret data, where data can lead you awry, and just be a better consumer in the future. So we will practice with this stuff in class.